ground pulled in the feed conduit is a better practice and should be done in addition to grounding the control cabinet to the building steel. Firstly, electrical code requirements such as the National Electrical Code, or NEC, require that all electrical circuits have a proper ground path. This is to ensure safety in the event of a fault or leakage current. Secondly, a ground in the feed conduit provides a low resistance path for fault currents to flow back to the source. This helps protect personnel and equipment from electrical shocks and fires. Thirdly, grounding the feed conduit helps reduce electrical noise and interference, which can affect the operation of electronic devices in the control cabinet. Fourthly, in the event of a power surge or lightning strike, a ground in the feed conduit can help protect the equipment in the control cabinet by diverting excess voltage to ground. Fifthly, variable frequency drives, or VFDs, rely on a stable ground reference to function properly. A ground in the feed conduit ensures that the VFD is a proper ground reference, which can help prevent undervoltage faults. While grounding the control cabinet, the building steel provides a path for fault currents. It is not as reliable as grounding the feed conduit. Building steel can have higher resistance than dedicated grounding conductors, which can limit the effectiveness of the grounding system. Therefore, it is recommended to both ground the control cabinet to the building steel and pull the ground conductor in the feed conduit to ensure a proper and safe grounding system. The importance of a proper grounding system within a control cabinet that feeds variable frequency drives, VFDs, cannot be overstated. These drives, which are used to control the speed of electric motors, are sensitive to voltage fluctuations and electrical noise. A stable and reliable ground is essential for their correct operation and to prevent faults such as the undervoltage trips mentioned. Examining the requirements outlined in the National Electrical Code, or NEC, it becomes clear that a dedicated ground path is not just a best practice but a code requirement. The NEC mandates that all electrical circuits have a grounding conductor to ensure safety and provide a low impedance path for fault currents. This path allows protective devices like circuit breakers to quickly trip and de-energize the circuit in the event of a fault, minimizing the risk of electrical shock and fire. The ground in the feed conduit serves as this dedicated path, ensuring that any fault current can flow back to the source with minimal resistance. The primary function of a grounding system is safety. By providing a low resistance path for fault currents, the ground conductor in the feed conduit helps to quickly clear faults, preventing dangerous voltage from appearing on equipment enclosures or other conductive parts. This significantly reduces the risk of electrical shock to personnel who may come into contact with the equipment. In addition to safety, proper grounding also plays a critical role in reducing electrical noise and interference. Control cabinets often house sensitive electronic equipment, including the VFD themselves, which can be susceptible to electrical noise generated by other equipment or external sources. Grounding the feed conduit helps to create an equipotential plane, minimizing voltage differences between different parts of the system and reducing the amplitude of electrical noise. This can improve the reliability and accuracy of the control system. Overvoltage protection is another important benefit of a properly grounded system. In the event of a power surge or lightning strike, the ground conductor in the feed conduit provides a path for the excess voltage to dissipate to ground, protecting the equipment in the control cabinet from damage. This is particularly important for VFD, which can be damaged by even relatively small overvoltage events. VFD rely on a stable ground reference to function properly. The ground conductor in the feed conduit provides this reference, ensuring that the VFD can accurately measure and control the voltage and current supplied to the motor. Without a proper ground reference, the VFD may experience undervoltage faults, erratic behavior, or even damage. Grounding to building steel can provide a path for fault currents. It is not as reliable as grounding the feed conduit. Building steel can have higher resistance than dedicated grounding conductors, especially at the frequencies associated with fault current. This higher resistance can limit the effectiveness of the grounding system, potentially delaying the clearing of faults and increasing the risk of electrical shock. Furthermore, building steel may not be continuous or properly bonded throughout the structure, which can further compromise its effectiveness as a grounding path. For these reasons, It is always recommended to pull a dedicated ground conductor in the feed conduit, in addition to grounding the control cabinet to the building steel. This ensures a proper and safe grounding system that meets the requirements of the NEC and provides the best possible protection for personnel and equipment. The size of the ground conductor in the feed conduit must be properly sized according to the NEC. The size of the ground conductor must be based on the size of the ungrounded conductors in the circuit. The NEC provides tables that specify the minimum size of the ground conductor for different circuit sizes. It is important to consult these tables to ensure that the ground conductor is adequately sized to carry the maximum fault current. In addition to the size of the ground conductor, the type of conductor must also be considered. The NEC specifies that the ground conductor must be made of copper or other approved material and must be insulated or bare. If the ground conductor is insulated, it must be identified by a green color or a green color with one or more yellow stripes. The installation of the ground conductor is also important. The ground conductor must be installed in the same conduit as the ungrounded conductors and must be connected to the equipment grounding terminals in the control cabinet and at the source of the power supply. The connections must be made with approved connectors and must be tightened to the proper torque to ensure a good electrical connection. Regular inspection and testing of the grounding system is essential to ensure that it is functioning properly. The grounding system should be inspected for any signs of damage or corrosion and should be tested to verify that it is providing a low resistance path to ground. The testing should be performed by a qualified electrician using appropriate test equipment. In summary, a ground pulled in the feed conduit is a critical component of a safe and reliable electrical system for VFD control cabinets. It provides a low resistance path for fault current, reduces electrical noise, protects against overvoltage, and ensures proper VFD operation. While grounding to building steel can provide some level of protection, it is not as reliable as a dedicated ground conductor in the feed conduit. Therefore, it is always recommended to pull a ground conductor in the feed conduit, in addition to grounding the control cabinet to the building steel, to ensure a proper and safe grounding system. The National Electrical Code, or NEC, provides specific requirements for grounding electrical systems. Article 250.4 A5 states that the grounding electrode conductor shall be used to connect both the system grounded conductor and the equipment grounding conductors at the service equipment or at the source of a separately derived system. 250.4 A1 also mentions that grounding electrical systems reduce the voltage on the electrical system with regards to ground, reducing the chances of shock. A proper grounding system has several key characteristics. Firstly, low impedance is necessary. The grounding path should have low impedance to facilitate the flow of fault current and enable overcurrent protection devices to operate quickly. Secondly, the grounding conductor should be sized correctly. The size of the grounding conductor must be adequate to handle the anticipated fault current. The NEC provides guidelines for proper sizing based on the size of the ungrounded conductors. Thirdly, secure connections are also necessary. Grounding connections must be mechanically sound and electrically conductive to ensure a reliable path to ground. Fourthly, continuity is important as well. The grounding path must be continuous from the equipment back to the source to provide a reliable path for fault current. And fifthly, proper installation is necessary. Grounding conductors must be installed in accordance with the NEC and other applicable standards. When troubleshooting VFD undervoltage faults, it is important to consider the grounding system as a potential cause. Firstly, visually inspect the grounding system. Check for loose connections, corroded conductors, and other signs of damage. Secondly, use a multimeter to measure the resistance of the grounding path. The resistance should be as low as possible, typically less than 1 ohm. Thirdly, perform a ground impedance test. This test measures the impedance of the grounding path at different frequencies. A high impedance can indicate a problem with the grounding system. Fourthly, check for ground loops. Ground loops can cause noise and interference that can affect the operation of VFD. And fifthly, verify the grounding electrode system. Ensure that the grounding electrode system is properly installed and connected to the building grounding system. In addition to the ground and the feed conduit, other grounding practices can also improve the performance and reliability of VFD systems. Firstly, bonding all metal parts of the control cabinet together is important. This creates an equipotential plane that minimizes voltage differences and reduces electrical noise. Secondly, using shielded cables for power and control wiring can also make a difference. Shielded cables help to reduce electrical noise and interference. Thirdly, installing line reactors or filters at the input of the VFD helps to reduce harmonic distortion and improve power quality. Fourthly, surge suppressors are important for protecting the VFD from voltage transients and surges. Fifthly, regular maintenance and inspection of the grounding system is also necessary. This helps to identify and correct any problems before they can cause equipment damage or safety hazards. Considering the NEC, specifically section 250.96. A. It states that bonding equipment must be provided to ensure electrical continuity and the capacity to conduct safely any fault current likely to be imposed. This further supports the requirement for a robust grounding and bonding system for VFD control cabinets. The undervoltage faults may arise from various factors. Firstly, line voltage fluctuations can cause undervoltage faults. Secondly, the overload conditions may also be a factor. Thirdly, loose connections in the power supply or motor wiring may contribute to undervoltage faults. Fourthly, there might be issues with the VFD programming or parameters. Fifthly, the improper motor sizing for the application can also result in undervoltage faults. Sixthly, the excessive harmonic distortion in the power system may affect the voltage stability and cause undervoltage faults. Finally, there may be external factors such as utility power quality issues affecting the incoming voltage supply. Understanding the root causes of undervoltage faults is essential for implementing effective solutions. This involves carefully examining the electrical system, motor characteristics, VFD settings, and external factors to identify the underlying issues and prevent future occurrences. In addition to the grounding system, the power quality of the incoming supply can also affect the performance and reliability of VFD systems. Firstly, harmonic distortion can be a problem. Excessive harmonic distortion can cause voltage fluctuations, overheating of equipment, and misoperation of electronic devices. Secondly, voltage imbalances can also affect VFD performance. Voltage imbalances can cause motor overheating, reduced efficiency, and increased vibration. Thirdly, voltage sags and swells can also cause problems. Voltage sags and swells can cause VFD to trip or malfunction. Fourthly, transient voltages can also affect the system. Transient voltages can damage sensitive electronic components in the VFD. To improve power quality, several measures can be taken. Firstly, install harmonic filters to reduce harmonic distortion. Secondly, use voltage regulators to stabilize voltage fluctuations. Thirdly, install surge suppressors to protect against transient voltages. Fourthly, perform regular power quality monitoring to identify and correct any problems. The effectiveness of a grounding system is greatly influenced by the soil conditions. Firstly, the soil resistivity plays a significant role. High soil resistivity increases the impedance of the grounding path, reducing its effectiveness. Secondly, the moisture content of the soil also matters. Dry soil has higher resistivity than moist soil, which can impair grounding performance. Thirdly, the type of soil also influences grounding. Sandy soil typically has higher resistivity than clay soil. Fourthly, the temperature of the soil can also affect grounding performance. Frozen soil has significantly higher resistivity than unfrozen soil. To improve grounding in poor soil conditions, several methods can be employed. Firstly, using multiple ground rods can help. Installing multiple ground rods in parallel reduces the overall resistance to ground. Secondly, the ground enhancement materials can also make a difference. Adding ground enhancement materials such as bentonite or conductive concrete can improve soil conductivity. Thirdly, the deep grounding techniques can also enhance the ground. Driving ground rods deeper into the earth can reach more conductive soil layers. Fourthly, the ground grades can also assist in grounding. Installing a grid of interconnected ground conductors can improve the overall grounding performance. In summary, a proper grounding system is essential for the safe and reliable operation of VFD control cabinets. The ground in the feed conduit provides a low resistance path for fault currents, reduces electrical noise, protects against overvoltage, and ensures proper VFD operation. While grounding to building steel can provide some level of protection, it is not as reliable as a dedicated ground conductor in the feed conduit. Therefore, it is always recommended to pull a ground conductor in the feed conduit, in addition to grounding the control cabinet to the building steel to ensure a proper and safe grounding system. Remember to follow the NEC guidelines and consider the specific requirements of your application when designing and installing a grounding system. Regular inspection and maintenance are also crucial for ensuring the long-term effectiveness of the grounding system. The information presented is intended for general guidance only and should not be substituted for professional engineering advice. Consult with a qualified electrician or engineer for specific recommendations regarding your electrical system. The importance of a robust grounding system extends beyond the immediate safety and operational benefits. It also contributes to the overall longevity and reliability of the VFD and associated equipment. A well-grounded system minimizes stress on components caused by voltage transients and electrical noise, reducing the likelihood of premature failure. Furthermore, a stable ground reference ensures accurate control and reduces the risk of erratic behavior or misoperation, which can lead to process disruptions and costly downtime. When evaluating the existing grounding system, consider the following factors. Firstly, the age of the system is important. Grounding systems can degrade over time due to corrosion, loose connections, or physical damage. Older systems should be thoroughly inspected and upgraded as necessary. Secondly, the environmental conditions also matter. Systems exposed to harsh environments such as corrosive atmospheres or extreme temperatures may require more frequent maintenance and replacement. Thirdly, the changes in the electrical system should also be kept in mind. Any modifications or additions to the electrical system can affect the performance of the grounding system. It is important to re-evaluate the grounding system whenever changes are made to ensure that it is still adequate. Fourthly, the industry standards are also essential. Grounding systems should comply with the latest versions of the NEC and other applicable industry standards. Staying up to date with these standards ensures that the system is designed and installed according to best practices. Finally, the available documentation is helpful. Proper documentation of the grounding system, including drawings, test results, and maintenance records, can facilitate troubleshooting and future maintenance. In cases where undervoltage faults persist despite proper grounding, other potential causes should be investigated. Firstly, the incoming power supply should be examined. Check the voltage and frequency of the incoming power supply to ensure that it is within the VFD operating range. Secondly, the motor characteristics must also be examined. Verify that the motor is properly sized for the application and that its nameplate data matches the VFD settings. Thirdly, the VFD parameters should also be checked. Review the VFD programming and parameters to ensure that they are correctly configured for the motor and application. Fourthly, the wiring connections must be verified. Inspect all wiring connections for looseness, corrosion, or damage. Fifthly, the load characteristics must also be considered. Analyze the load characteristics to identify any unusual patterns or conditions that could be causing undervoltage faults. Sixthly, the ambient temperature must also be kept in mind. High ambient temperatures can reduce the VFD performance and increase the likelihood of faults. Finally, electromagnetic interference, or EMI, should also be examined. Identify and mitigate sources of electromagnetic interference that could be affecting the VFD operation. Addressing these factors in a systematic manner can help to identify and resolve the root cause of the undervoltage faults. Remember to consult with qualified professionals for assistance with complex troubleshooting or repairs. In addition to the technical aspects of grounding, it is also important to consider the human factors. Firstly, training and education for employees is a must. Provide training and education to employees on the importance of grounding and the proper procedures for working with electrical equipment. Secondly, the awareness and communication should also be considered. Promote awareness of grounding safety among all employees and encourage them to report any potential hazards or concerns. Thirdly, the safety procedures must be followed. Establish and enforce safety procedures for all electrical work, including lockout-tagout procedures. Fourthly, the use of personal protective equipment, or PPE, should be emphasized. Require the use of appropriate personal protective equipment, such as gloves, safety glasses, and insulated tools when working with electrical equipment. By addressing both the technical and human factors, you can create a safer and more reliable electrical system for your VFD control cabinets.